Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to learn the topics of sampling theory and linear regression analysis. In this module on sampling theory with R software, we are going to continue with our chapter Stratified random sampling. So in the last lecture, we started a discussion on stratified random sampling, and I had given you a fair idea that under what type of conditions the stratified random sampling can be used. Now, in this lecture I will move forward and we will see how we can estimate the population mean and population variance, and how they can be used in the construction of confidence interval. Okay, so let us begin our lecture, but let me try to take the slide of the last lecture to explain you some more things. So, you may recall that we had used these symbols, that we have a population of size capital N, which is divided into say k different non-overlapping, they are non-overlapping groups, or they are called as strata, or this is stratum number 1, stratum number 2 and stratum k. So, all those units of population are divided in this case strata. They have been divided in such a way such that within group they are, the sampling coordinates are homogeneous with respect to the characteristics under study, and when we try to say between groups, between strata, they are heterogeneous as far as possible. So, remember just remember within homogeneous as far as possible and between heterogeneous as far as possible. Right. So, now these capital N units are divided in capital N1 units, N2 units, Nk units. So, capital N and I, this is going to denote the number of units in the ith strata, and from there we can use the SRS either WOR or say WR to draw the samples, and from the stratum 1 we draw a sample of size small n1 number of units from capital N1 number of units, and in the second sample we try to draw say small n2 number of units from a population of size capital N2 number of units, and so on. Now, the issue comes here. Based on the sample number 1, we have obtained here the sample mean y1 bar. Based on sample number 2, we have computed the sample mean y by 2, and similarly from the kth sample we have computed the kth sample mean. But what is your objective? Your objective is not to consider this k different sample means, but you are more interested in getting a single value. That means, you want to combine all this y1 bar, y2 bar, yk bar, and you want to combine them in such a way such that their combination gives you a good estimator of the population mean which exists somewhere here. So, one option to combine the different sample mean is to consider the weighted arithmetic mean. Well, there can be other approaches also, but this idea is coming from the statistical inference, that if you try to consider the values of different weighted arithmetic mean, and means you try to choose those weights in such a way so that they are computable, and the resultant estimator gives you a good value of the population parameter. So, with this objective we move forward, and first let us try to fix our notations and symbols. So, I am going to use here capital N to denote the population size. So, there are capital N number of sampling units. and from these capital N number of units, we will create capital K number of strata. That means, this population of size capital N is going to be divided into, say, different strata, one number is strata 1, strata 2, up to here strata K. And what is here capital Ni? Ni is the number of sampling units in the ith strata. And if you try to sum all the strata sizes, then it will give us the total sample population size. And similarly, from each of the strata, you try to draw the sample. So, this small Ni is the number of sampling units to be drawn from the ith stratum, and the sum of all N1, N2, Nk will give us the total sample size. So, that is going to be our notation during the stratified sampling lecture. And let this capital Y denote the characteristic under study, for example, say height or weight or age or anything else. And small yij is going to denote the value of the jth unit in the ith stratum. This means here what? For example, if you have here a population, you are dividing this into some samples. So, now there is some unit, say y1, some unit y2. Now, this unit may be classified here, say for example, say in stratum number 1, and y2 may be divided into, say, stratum number 2. So, once it comes here from there, now this unit will have two addresses. First address is that when it is included in the stratum, whether this is the first unit to be included in the stratum, or second unit, or say jth unit. So, this j will go from 1 to Ni, means Ni is the number of observations which are drawn from the ith strata, right. So, here is our sample, somewhere here it will be yij, and then the second address will be whether this y1 is going to, say, stratum 1, stratum 2, or say stratum k, right. So, yij is going to denote the value of the jth unit in the ith stratum. And now, we try to find out the mean of all the units in the ith stratum. So, the mean of ith stratum, that is the population mean of ith stratum, will be denoted by y bar I, and this is going to be the sum of all the units which are present in the ith stratum, right. So, this is denoted by 1 upon Ni, j goes from 1 to capital Ni, yij. And similarly, whatever are the units which are drawn from the ith stratum, they are denoted by y bar I, say small y bar I, which is 1 upon small Ni, summation j goes from 1 to Ni, yij. So, this is the sample mean of the units which are drawn from the ith stratum. And then capital Y bar. Capital Y bar is the population mean, which is the mean of all the units in the population, capital Y1, capital Y2, up to capital Yn. But here in this case, we are not considering the simple arithmetic mean to indicate the capital Y bar, but we are denoting here a weighted arithmetic mean. So, this weighted arithmetic mean is given by 1 upon capital N, summation I goes from 1 to k, Ni y bar I, right. So, I can write down this quantity as here, say summation I goes from 1 to k, and then it will be here, say here Ni upon here N times here y bar I. So, this Ni upon N I am trying to denote by here Wi, right. Okay. So, now, from every strata we try to draw a sample independently. So, ultimately what we will have? We will have k independent sample which are drawn by simple random sampling from each of the stratum. So, and each independent sample will yield one value of the sample mean. So, there will be k estimator of the parameter population mean, but our ultimate objective and goal is to have a single estimator. So, the question comes here, how to combine those different k sample information together into one estimator, which is good enough to provide the information about the parameter. Here at this stage, I would like to inform all of you that when we are trying to deal in statistics, there is a topic what we say this combining different sample information, that is itself a topic in statistics where people try to address that how different type of sample information can be combined together to give a good outcome. So, in the case of stratified sampling, as we have discussed, the population mean is defined as the weighted arithmetic mean of stratum means, right. So, now this weights are actually known to us. So, this capital Ni is known to us, capital N is known to us. So, the weights Wi's are known to us. Now, we try to find out the sample mean of all the units which are drawn from each stratum, and we try to find out their weighted arithmetic mean, and this is called as stratified mean. This stratified mean is defined here like this y bar st, which is 1 upon capital N, I goes from 1 to capital K, capital Ni times y bar I. Right. So, here the weights are obtained using the size of the stratum Ni divided by N. Well, there is always a question from the students at this stage, why are we using the size of the stratum? Why not are we using the weights as say size of the sample, say small Ni upon say N. So, I will try to address this thing in the next couple of slides. Okay. So, now we have defined that this is our estimator y bar st, that is going to estimate the population mean. The story behind this thing, that why can't we use the weighted mean of sample median, sample mode or something else, that reason goes to the say first couple of lectures when we started the discussion on simple random sampling, right. So, I will not repeat it here again, but now we have got here an estimator which we are proposing, that which is to be used to find out the population mean, right. So, we would like to study its property, whether this estimator is good or bad, and based on that we will make our recommendation. Now, before we try to understand or before we try to do the algebra in this topic, I would like to just tell you something. You see, we already have done all the algebra very carefully during the simple random sampling. I have shown you how to prove unbiasedness, how to find out the variances or their estimates. And since here we are using simple random sampling, so I can use those results here directly. For example, when I say I have a stratum of size capital Ni, from there I am trying to draw here a small sample of size small Ni by SRS. It can be WR or WOR. That means, if I ask you that what will happen if I try to consider this ith sample mean as my sample mean and this ith stratum as my population. Obviously, we are trying to draw the sample by simple random sampling. So, we already have proved that this is going to be an unbiased estimator. So, I do not need to prove it again. The only thing I have to prove that if I try to combine them using the weights Wi, then what will happen. Similarly, when we try to find out the variance, we already have proved that if you try to take this thing as a sample which is drawn from the ith stratum, then and if you try to consider this stratum as a population, then we know what is the expression and how we can find out the expression for the variance of y bar, that is the sample mean, when we are trying to draw a sample of size small n from a population of size capital N. So, I do not need to prove them again, and that was the reason that I had given you details in those cases. But it does not mean that I am going to give you here all the proofs. As I declared in the beginning itself, I will try to give you those proofs which I can handle here easily and which are essential for the development of the course and to explain you the concept. There are many results, for example, in this stratified sampling also which are important. So, I will tell you those important results, and some results I will refer you to some other books or courses. So, we will try to do in this way, right. So, let us now start our discussion. Since the sample in each of the sample is being drawn by simple random sampling, so obviously if you try, so if you have learned that if you have a population of size capital N and if you draw the sample of size small n, then expected value of y bar here is capital Y bar. Now, what I am asking you, now your population size is Ni, capital Ni, and your sample size is small ni. Based on that, your sample mean is y bar I. So, do not you think that this is automatically going to be an unbiased estimator of capital Y bar I? Answer is yes. So, why not to use this information correctly and intelligently? So, now I try to find out the expected value of y bar st. So, that is going to be 1 upon capital N, I goes from 1 to k capital Ni, and this expectations operator which comes inside the summation sign. So, now I know this expected value of y bar I is nothing but your y bar I. So, I try to substitute it here, and if you try to see this quantity 1 upon capital N summation I goes from 1 to k Ni yi y bar I, this is nothing but your capital Y bar, which is the population mean. So, in this case y bar st is an unbiased estimator of y bar. So, this y bar st has got nice property that it is unbiased. Now, what is the meaning of unbiased? So, now we have got good estimator, but now first I try to address the question which I raised earlier, that in this case we have obtained an estimator of population mean by considering the weighted arithmetic mean y bar I, where your weights are given by capital Ni upon n using the stratum size. Now, suppose I say that instead of stratum size, I try to use here sample size, say, and I write down the new weights as small Ni upon n. So, in this case, if I try to define here a y bar, this will become here I goes from 1 to k, say Wi star times here y bar I. So, this becomes here I goes from here 1 to k Ni upon here n y bar I. So, what will now happen to this estimator, that we have to see. So, this is the same estimator which I have written here. Okay. So, now once I try to check the unbiased behavior of this estimator, we know that expected value of y bar I will be equal to capital Y bar I. Now, once I take this expectation sign operator inside the summation sign while finding out the expected value of y bar, this expected value of y bar I will be nothing but your capital Y bar I. And then you can see here this expression is not the same as the value of capital Y bar which you have defined. Now, in case if you argue that okay, I can define the population mean by this thing I goes from 1 to k Ni y bar I, possibly this is not correct, because you are taking only here Ni observation which are not representing the population. The population has capital Ni observation in every strata, and you are choosing only the selected number of observation from every strata to indicate the population mean, which is itself contradictory. So, expected value of small y bar does not comes out to be y bar. So, I can say here y bar is a biased estimator of population mean capital Y bar, and that is the reason we do not consider y bar, but we consider here y bar ST as a good estimator for estimating the population mean. Now, I try to find out the variance of this y bar ST. So, remember one thing, I will just write down here for your convenience. Y bar ST is I goes from 1 to k Wi square, sorry, Wi y bar I. And if you try to take out, try to operate the variance operator, and if you try to find out variance of y bar ST, this will come out to be I goes from 1 to k Wi square variance of y bar I, and double summation I not equal to j. This will be Wi Wj covariance between y bar I and y bar j. So, now you can see here, this is the covariance between the ith and jth sample, and ith and jth sample have been drawn independently. In fact, all the samples have been drawn independently of each other from all the strata. So, this covariance will become 0. So, that is what I am trying to write down here, that covariance between y bar I and y bar j will be 0, and when you are trying to draw a sample of size Ni from a population of size capital Ni by suppose SRS WOR, then we know that earlier the variance was given by n minus n upon n s square. Now, I can make it here, because this is coming from ith strata, this will become Ni, this will become small Ni, this is here capital Ni small Ni, and s square will become capital Si square, right. So, this is exactly what I am trying to do here, that is the variance of y bar I from the ith strata, that is the variance of the sample mean from the ith strata will be denoted by this quantity, right. And what is here S square or Si square? If you remember, S square was earlier the variance of the population which is in the capital Ni. So, now I have to rewrite this S square as earlier it was S square was n minus 1, j goes from here 1 to n, yi minus y bar whole square. Now, I will try to rewrite this definition for the ith strata. So, this S square becomes Si square and capital N becomes Ni, and this yi becomes yij, and this y bar becomes y bar I. So, this is here the definition of Si square. So, now you can see here you have obtained all this expression, and you simply have to use this expression over here, and you will get the expression, right. So, I can just substitute that expression over there, and you can see here just substituting it here, I get the variance of y bar ST under SRS WOR like this, right. One thing you can observe here, that this same quantity I can write down here as say Wi square 1 minus small Ni upon capital Ni. If you remember, we had denoted small n by capital N as a sampling fraction. So, this I can write in this particular way also, right. Okay. Now, at this address I will try to show you that why it is recommended to construct the strata in such a way such that they are within homogeneous and between heterogeneous. You can see here in this expression, this is the variance of y bar ST under SRS WOR. This quantity here is fixed, that you cannot control, because Wi is Ni upon n, right. Now, there are only two things remaining which you have not controlled. Capital Ni, it is not in your control, that means once you have created the groups, the stratum size is fixed. Now, there are two things here, Ni and Si square. At this moment, for a while we are assuming that Ni is fixed. Somehow means you have followed a rule and you have obtained the sample size. So, the only quantity which is left to us is Si square. Although I will also try to address that this small Ni can also be controlled, but that will come later. At this moment, I am assuming that this is fixed. Those who have knowledge of stratified sampling, they can imagine that the sample size can be obtained by different types of allocations, equal allocation, proportional allocation, Neyman allocation, and there are various things. But at this moment, I am assuming that they are fixed. So, now only Si square is left in this quantity which is to be controlled. Obviously, now if this Si square is small, then it will make the variance of y bar st also smaller. So, I have written here very clearly, if Si square is small for all i's, means the capital Si square for first strata, second strata, kth strata, if all of them are say small, then the variance of y bar st will also be small. Note that if one of the Si square is very large, possibly that will also disturb. So, ideally I would say that if all Si squares are smaller, then variance of y bar st will also be smaller. Now, what does this mean? When I say Si square is small, what does this mean? Try to think, try to take a pause of this video and try to think for a couple of minutes and then start the video. Right. So, when I say Si square is small, that means the variability within the ith group is smaller. Then the variance of y bar st will be small. So, this is the reason that the strata are constructed in such a way such that the within group variability is as small as possible. And then obviously, the variability among the strata, that will automatically become larger. So, that is the reason. So, now you can see here I have established that why you have considered the form of y bar st to be like summation capital Ni into y bar I upon capital N, because this estimator has been constructed in such a way such that it will give you a value of the population mean with a smaller variability. Yes, one can think about different other estimators also, and that is one of the area of research in sampling theory where people try to find out better estimator who have got smaller sampling variability. Right. Okay. Now, once you have obtained this variance of y bar st here, obviously this depends on the population value capital Si square. So, you cannot estimate it on the basis of given sample of data. So, now we need to find out the estimate of variance of y bar st. But now it is not difficult, because you already have drawn the sample from the ith strata by SRS WOR, and for that you already have proved during the lectures on simple random sampling that expected value of small Si square is capital Si square in case of SRS WOR, where this Si square is simply the value of S square in the ith sample. Once that is there, so I can replace this quantity capital SI square by SI square. So, the estimate of variance of y bar I will come out to be directly from the SRS WOR, that is Ni minus Ni upon Ni small si square, and I try to replace it here. So, the variance of y bar St hat will become j goes from 1 to k Wi square, the variance of y bar I hat, and this I can replace here. So, this quantity here summation I goes from 1 to k Wi square Ni minus Ni upon Ni Si square, small si square. This is an estimate of the variance. So, once you have a sample, you can also estimate the population variance of y bar St, and if you take the positive square root of this variance estimator, then you will get the standard error. The issues which are related in defining the standard error that I already have discussed in the earlier lecture, so I will not repeat it again. Now, I come to another aspect. Suppose somebody decides that instead of drawing the sample by SRS WOR from the ith stratum, suppose the decision is to draw the sample by SRS WR, simple random sampling with replacement. In that case, what will happen? So, let us try to find out the things. So, in this case also the y bar St will remain the same. This is the same definition, but if you try to find out the expected value of here y bar St, this will become here I goes from here 1 to k Wi, and expected value of y bar I, and expected value of y bar I here is capital Y bar I. So, this quantity is nothing but your capital Y bar. So, under this case also y bar St remains is an unbiased estimator of population mean capital Y bar. So, there is no change in the unbiasedness character of y bar St. For finding out the variance of y bar St under WR, in the case of SRS WR, we know that the variance of y bar was obtained as n minus 1 upon n s square. So, once I try to use it here for the ith strata, that means is a sample of size small Ni is obtained from of the stratum of size capital Ni. So, this capital N will become Ni and small n will become small ni, and s square will become the variance of the ith stratum. So, this is what I have written here, and I simply replace the variance of y bar I by here this quantity, and you can see that this quantity is nothing but your summation Wi square sigma I square upon Ni. Yeah, if you remember, we had used this relation that n minus 1 s square is equal to n times sigma I square, right. And if you want to find out an unbiased estimator of variance of y bar st, so you may recall that we already had proved that expected value of Si square or expected value of here S square is equal to sigma I square. So, in the case of stratified sampling, expected value of Si square will become say sigma I square. So, I can simply replace here sigma I square by this Si square, and you can see here an estimate of the variance of y bar st can be obtained by summation I goes from 1 to k Wi square small Si square divided by small ni, and sigma I square can be defined exactly on the same line as we have defined capital Si square. And if you want to find out the standard error, simply take the positive square root of this estimate of variance. Now, I try to address the issue of confidence interval estimation or population mean in case of stratified random sampling. Well, it is not so straightforward as in the case of simple random sampling, because when we are trying to find out the confidence interval, if you remember, we need to find out here a critical value which are here on the x axis corresponding to the distribution. And usually the values of sigma I square, or in case of stratified sampling the value of sigma I square are not known to us. So, we try to estimate them, and when we are trying to estimate them, then the properties of the y bar st changes, and this change is quite different what happens in the case of simple random sampling, because we are trying to combine it together. So, first of all we have to make an assumption that y bar st is normally distributed, and the standard error of y bar st is well determined, so that the critical value, say t, I am not really saying that this is the t distribution, but that I will show you that this is a critical value. This critical value can be read from the normal distribution table. And second thing is this, if you remember, the distribution of t also depends on the degrees of freedom. So, in case if only a few degrees of freedom are provided by each stratum, then t values can be obtained from the table of student t distribution. But this itself has an issue which I will try to address in the next slide. But suppose we assume that all these things are possible, and under that situation an approximate confidence interval can be computed by this expression, that y bar st plus minus t times standard error of y bar st. But if you try to see, this is not so straightforward. Why? Because the distribution of standard error of y bar st is not so simple. Well, that is the job of the statistician to find out all these things, but I am not giving you here all the details. But as a data scientist, you must know that what is the problem, what is something is happening, that you must know, so that you know that how much amount of mistakes you are going to make in your computation, and what are the violation because of which this error is coming, and how this violation can affect your final conclusion. In case if you assume that all the observation yij's they are coming from a normal distribution, then an approximate method for assigning the effective number of degrees of freedom to the distribution of standard error of y bar st. That means why I am calling is effective number, because you see the degrees of freedom are always some integer value, and here the distribution of standard error becomes too complex. So, it is not possible to get the exact number of degrees of freedom. So, we try to approximate it, and when we try to approximate it, the approximated value may not come out to be always an integer. So, that is why the value which we are going to estimate, that is called as effective number of degrees of freedom. So, the number of effective degrees of freedom, which is denoted by here small n, this is obtained by this expression, where this SI square you know, which is the variance from the ith sample, and this quantity here Gi is defined here like this. And so, if you try to compute here any, and then try to choose the value of any which is between minimum values of, say, all the ni minus 1 and summation I goes from 1 to k ni minus 1. So, whatever you get here, this value of any, try to choose this one, and this value will lie between these two limits. Right. Okay. So, in this lecture we have understood that why we have chosen this y bar st to estimate the population mean, and how to obtain the standard errors which are needed in a real life data, and then after that how to construct the confidence interval. One important aspect which you have learned, that whatever are the decisions, for example, the question which I raised in the beginning, that whether the stratum or the strata are constructed in such a way that they are within homogeneous or between heterogeneous, these types of questions can be answered using the statistics, using the statistical concepts. And these are the rules which govern us, that how we can construct an estimator for the population mean under different types of sampling scheme. So, if you go for cluster sampling, if you go for systematic sampling, the estimator to estimate the population mean will be different. They are not going to be always the same as, say, small y bar as in case of simple random sampling, or y bar st in case of stratified random sampling. Well, these estimators are not coming from sky. Well, as a statistician, this is the job that people try to construct different types of estimator, they try to find out their variances, and then they try to see which one is working better. And after making so much of efforts, they come up finally with the good solution, which I have given you here. So now, while constructing the strata, there were two variables, the sample size from the ith strata and SI square. So I already have addressed that how to control the variability of y bar st using SI square, but I assume that Ni is somehow known to us. In the next lecture, I will try to work with small ni, and we will try to see there are different ways which can give rise to different types of sample sizes to be chosen from the strata. And then it is possible that the variance of y bar st will be further reduced. So now you can see you have an estimator. If you do not want to do anything, just use it, but if you want to make the variability as small as possible, try to first construct the strata, and then after that you have one more option, that you can decide that how much sample I can draw from every stratum, so that the final variability in my estimator is as small as possible. So in the next turn, I will try to address the issue of sample selection. So you enjoy your lecture, you revise it, you study it, and I will take a leave. Till then, goodbye.